Hi everyone, how's it going? In this Mechanics of Solids, Mechanics of Materials video, I'm going to go through looking at the stress that's developed in a beam in bending and looking at how we show that on an element representing a couple of points in the beam. All right, so let's have a look at the problem. Okay, so here we have the problem. We've got a beam supported at the right-hand end by a pin support, and then at somewhere between the load and the end there is a roller support, and given this load and the beam being in bending, we want to know what the stress that's developed at points A and B will be, and also to show that stress on a differential element located at points A and B that represents those points. Okay, so if we look at this problem, we can hopefully see that the beam is going to bend something like this. So hopefully see that on the top here, it's going to be in tension. Top side's getting the fibers on the top side there are getting longer, whereas on the bottom they'll be getting shorter and being in compression. All right, so let's have a look at the problem. So firstly, let's draw a free body diagram. We've got our load P out here. At the right-hand end, at the pin support, if we imagine we take moments about the roller, for example, then we can see that the force out here needs to be acting downwards for it to be in equilibrium for moments, and then for some of the forces in the vertical direction to be equal to zero, we need the force at the roller support to be acting upwards. All right, so if we now, even though we've done this, let's go through the process of using our method of sections and taking a cut at the point where we want to know the stress. So we take an imaginary cut through point A here and then look at the internal actions. So we can see for equilibrium, we need an internal shear force, VA, and an internal bending moment, MA. And this time, not using the sign convention that we use when we're drawing shear force and bending moment diagrams, but just looking at the problem and seeing which way the moment goes. We can see that for equilibrium here, if we take moments about point A, this force out on the right here, the reaction force, is tending to cause a clockwise rotation. So therefore we need MA here to be anti-clockwise. Now, if you're thinking about your shear force and bending moment diagrams, we would have drawn this clockwise and then got a negative answer in our calculations. But for now, we're just going to look at the problem and say, okay, we can see from this that the moment here at A needs to be anti-clockwise. All right, so we can see that the beam bends like this. So the top fibers will be stretching, the bottom fibers will be in compression. So at point A here, we're going to have stress in tension. The other way that you can think about it is to look at the direction that the moment is going and say where the tail of the moment is coming out of the surface, that's in tension, and where the head of the moment is going, or the arc representing the moment going into the surface, that side will be in compression. So point A is in tension, and if we draw a little square element to represent that point, like that, we have point A, and the stress is normal to the surface. Right? So it's important that you know the direction of the stress relative to the beam itself and the cross section. So looking at this, you might be, wondering, well, which direction am I looking at? So what is this A really representing? One way to think about that is, we've got a little square in here that represents this. The other thing that we could do is to put on coordinate system. So if we call that horizontal direction X, longitudinal along the beam X, and then vertical direction we call that Y, then over here on our stress element we can put X and Y. So now we can see clearly that the stress at point A acts in the X direction. Okay, so longitudinal along the beam. All right, let's have a look at point B. So we've got our end load out here, put on our internal actions, shear force and a bending moment. So again, we're not using the positive sign convention that we used when we did shear force and bending moment diagrams. We're just looking at the equilibrium problem and saying which way does this moment need to go. So here we can see the force P tending to rotate anti-clockwise about point B. So our moment B is going to need to be clockwise. All right, so if we had been doing a shear force and bending moment diagram problem, and we'd put anti-clockwise here as our positive sign convention, we would have got negative for this moment. Right, but we've just put it on in the actual direction that it's going. Right, and we can see that at point B, because the arrowhead of our moment is acting into the surface there, right, also by looking at the considerations that we had up here about how it's being bent, we can see that the bottom here is in compression and the top is in tension. So we can do that, and then we can put our stress element to represent point B down here. Right, so point B is this little square here. Right, so I can also put on X and Y axes like I did here to make it more clear exactly what the direction of this stress is. All right, so that's the end of that problem. Hopefully that was helpful to you for understanding the direction of normal stresses due to bending. It's important that you know these, especially when you get to later problems where you've got lots of different components of bending. So here we've only got bending about one axis, but doesn't matter if it's about two axes on the surface. The normal stress that's developed from bending is, as its name suggests, normal to the surface. Right? So if you have a coordinate system like I just drew, with X coming out of the surface, so X being the longitudinal direction, then the stresses due to bending are always in that X direction. All right, that's it for now. See you next time.